Hello everyone, my name is Sami Al-Khairi and my talk is entitled Accurate Methods for the Design of Auditory Filters Based on Bandwidth and Delay Specifications. And I'll be talking you through each of these terms as we go through the talk. So first, let's start with auditory filter banks. So here what we have is Bode plots, so the magnitude and phase as a function of frequency for various plots for various filters in the filter bank. So each color corresponds to a separate filter. And you can see here that each filter might have a different peak frequency, it might have a different bandwidth, a different group delay, etc. Now let's focus on one of these filters. And what we can see here is, again, we have the magnitude and phase as a function of frequency or normalized frequency. And we can describe the behavior of this filter by stating the values of some filter characteristics. So we could say that it has some peak frequency, some convexivity at the peak, 10 dB bandwidth, 30 dB bandwidth, group delay at the peak, phase accumulation, equivalent rectangular bandwidth, etc. And collectively, I'm going to refer to these characteristics as filter characteristics. And this is the natural way in which we would describe the behavior of these filters. Consequently, it's the natural way we'd want to provide specifications on filter characteristics when designing auditory filters. So we might want to design an auditory filter with some value for the peak frequency, another value for the equivalent rectangular bandwidth, and we might also want to specify the value of 10 dB bandwidth. So our goal then is to develop methods to design auditory filters given specifications on filter characteristics. And if we do this, what this will allow us to do is mimic the behavior of certain species or certain pathologies. The other thing this would allow us to do is to systematically study how varying certain characteristics would alter the outcomes of perceptual models or technological contributions. So the question is, what do existing methods do? How do they design auditory filters? One method is the classical filter design method, set of methods, and these generally require a frequency response, specifying a frequency response over a length of frequencies along with a tolerance. So it's not based on filter characteristics, and hence it's not the natural specifications for auditory filters. A second choice may be a naive method based on second-order filters, which is an extrapolation to auditory filters and hence is not accurate. The third choice, which is most commonly used, is a method for gamma-tone filter design. Here you usually set the gamma-tone filter to be fourth order and then specify the equivalent rectangular bandwidth. However, when you fix this filter order, you've essentially reduced the number of degrees of freedom, and you've of course tied together your equivalent rectangular bandwidth with group delay and 3 dB quality factor, etc. Now, even if we do relieve this constraint of fourth order or fixed order, one issue with this method is that you have to specify filter order, which is not really a natural way of describing the behavior. All right, so what we want to do is to develop methods to design auditory filters based on filter characteristics, directly based on filter characteristics, and only based on filter characteristics, so no filter order coming into play. And we want to be able to specify simultaneous filter characteristics. So I might want to specify the value of the QERB and the group delay at the peak, or I might want to specify the 3 dB bandwidth and the 15 dB bandwidth. And lastly, of course, this should be accurate. Otherwise, there's no point in doing this. So let's think about how transfer functions are represented, how these filters are represented. And all I want to show you here is, this is a transfer function for one of the filters, and you can see that it's parameterized by some filter constants, A sub p, B sub p, B sub u, which don't really directly have any interpretation in terms of filter characteristics. There's no real interpretation in terms of filter characteristics here. And so, how do we get to this ability to design auditory filters given specifications and filter characteristics? Well, the natural thing we might want to try is to reparameterize the transfer function. So it's parameterized in terms of filter characteristics. So what we do is that we start out with our transfer function in terms of these filter constants. And some math later, we can reparameterize this in terms of sets of filter characteristics. So this is a reparameterization in terms of peak normalized frequency, phase accumulation, and group delay at the peak. And there's another example reparameterization in terms of peak normalized frequency, group delay at the peak, and convexivity at the peak. So these are examples that show that we've been able to reparameterize the transfer functions in terms of filter characteristics, which makes this a very direct way of designing auditory filters. And I've shown that it allows for simultaneous specification. So in all cases, we were dictating a few filter characteristics and not just one. And in fact, we can dictate various combinations of filter characteristics. So just to show you here, we might want to dictate the values of the combination of filter characteristics, like the normalized peak frequency, group delay at the peak, and quality factor based on the equivalent rectangular bandwidth, or maybe peak normalized frequency, 3 dB quality factor, or 10 dB quality factor, or any NDB quality factor really, and group delay at the peak. And so I've shown you here that we're able to design auditory filters directly based on simultaneous specifications and filter characteristics. And a natural question comes, what combination of filter characteristics should we use? And the answer is it really depends on what we're using or what we're designing the auditory filters for. So for instance, if we are interested in designing auditory filters that are sharply tuned but with limited group delay, or if we're interested in specifying and controlling the frequency selectivity and synchronization across filters in a filter bank, it makes sense for us to dictate a magnitude-based characteristic and a phase-based filter characteristic, like the combination of the equivalent rectangular bandwidth and group delay at the peak. Alternatively, if what we're interested in doing is having fine control over the shape of the magnitude of the frequency response, then it makes sense for us to specify two magnitude-based characteristics like the 3 dB bandwidth and the 15 dB bandwidth. All right, so coming back to our objective here, I've shown you that the methods for designing auditory filters do so directly based on simultaneous specifications and filter characteristics. The last thing that I want to show you is whether or not this is accurate. And here what I've done is that we've designed filters given some specifications, some specified values of filter characteristics. So here we're specifying peak normalized frequency, 3 dB quality factor, and group delay at the peak. And on the left here, you can see the magnitude and the phase or the Bode plots for the filter that was designed using these specifications. And let's concentrate on the blue line here. That's the P filter that I showed you earlier. And if we look at the right here, this is the percent relative error in these filter characteristics. So here we have the percent relative error in the 3 dB quality factor, and here in the group delay at the peak. And you can see for this set of filter characteristics values, the relative error here in the 3 dB quality factor is 1.5%, which is pretty good. And in fact, for another type of auditory filter, this error is in fact even lower. And based on what we've seen, this accuracy is, this method is still pretty accurate across the human cochlea, or what would mimic the human cochlea, base to apex. All right, so now I've showed you that we fulfilled our objective. And this is towards developing the characteristics-based method for direct design of auditory filters to address two critical needs. One is to accurately design auditory filters given simultaneous specifications and characteristics. And the other is to systematically study how varying characteristics affect the findings of perceptual models and technological advances. And the second one in particular may open the doors for some interest in future work or interesting collaborations. So specifically, one might want to say, okay, let me look at the, or let me determine what the isolated dependence on one of the filter characteristics, let's say the ERB is, while holding the group delay constant for certain studies or models. And we might want to start out with a few of the things mentioned here, like intelligibility scores of bandpass filtered speech, accuracy of speech recognition, sound source localization models, accuracy of speech intelligibility models for cochlear implants. And one other thing we might want to do in the future is to have the filter design methods incorporate or play along with some nonlinearity or quasi-linearity in order to be able to also study the effects for hearing loss simulations. So with that, I end my talk and open the floor to questions.